Now, okay. Good afternoon, everybody. Today is my great pleasure to have Professor Niu from Donghua University in China. And he is going to share us his recent result on the global dynamics of 3D Lotka-Volterra computation model. But this time with seasonal cessation. And he is going to show us how to classify the global dynamic by some index. And I am very curious about this result. So let's welcome him.
Thank you very much. Thank you for Professors Jia Yuan and Xu Shibi's invitation. In this talk, I will talk about the global dynamics of the 3D Lotka-Volterra competition model with the seasonal succession. This talk is mainly based on the recent joint work with Yi Wang, the University of Science and Technology of China, and Professor Xie Xizhuang from Huaqiao University. It is known that the seasonal succession is a prevalent environmental feature, which has an important impact on the growth and survival of species. Due to the seasonal succession, population experience a periodic environmental driven by both the internal dynamics of species interactions and the external seasonal forcing. There have been many studies on the impact of the seasonal succession, but mainly based on the experimental and the numerical research. Recently, the ecologist Klaus Meyer proposed a novel approach called it the successional state dynamics, and he and his collaborator studied the effect of the seasonal succession in the predator-prey model and also the seasonal forced food webs. Further, Professor Shibi Xu and Xiaoqiang Zhao proposed the Lotka-Volterra competition model with seasonal succession to study the effect of seasonal succession on the two competing species. Motivated by the Xu and Zhao's work, here we consider the three-dimensional Lotka-Volterra model with seasonal succession, which is described by the equation 1. Here, the parameter omega is represents the period of the season, and the parameter phi belong to 0 to 1 denotes the proportion of the season. In this model, it is assumed that in the bad season that for the time t in chi omega to chi omega plus 1 minus phi omega, it is assumed that the species decrease exponentially as described by the equation 1a. And in the good season, it is that is for the time t belongs to chi omega plus 1 minus phi omega to chi plus 1 omega. It is assumed that the species, the growth satisfies the Lotka-Volterra model as described by the equation 1b. Here we assume all the parameters bi, aij are positive constants, which describes the competing species. This model was first proposed by Xu and Zhao, following Clausius' approach. In fact, the model 1 can be written as a time-omic periodic Lotka-Volterra system, which is described by the equation 2, with discontinuous omega periodic coefficients bit and aijt. That is, the omega periodic function bit equals the constant minus mu I for the time t in the bad season, while it equals to the constant bi for the time t in the good season. And the periodic function aijt belong to equal to 0 for time t in bad season, and the constant aij for the time t in the good season. We denote by positive x to the solution of the system 1 through the initial point x. Because the system is periodic, we usually use the Poincare map P to study the long-term dynamics. That is, the map P is given by psi omega x, which is usually called the period map. The x is defined on an open set W containing the non-negative cone 0, infinity 3, which is denoted by R3+. Then the discrete time orbit pkx is just equal to psi k omega x. Here we are interested in the discrete dynamics deduced by pk in the non-negative cone R3+. Also, we let the linear map L to be x maps to e minus mu 1, 1 minus phi omega x1, e minus mu 2, 1 minus phi omega x2, e minus mu 3, 1 minus phi omega x3, which is just the solution of the equation 1a at the end of the bad time 1 minus phi omega. We will use phi tx to denote the solution map of the autonomous Lotka-Volterra model 4. Then, under these notations, the Poincare map px is written by phi, the capital phi, phi omega Lx. We first recall the results of Xu and Zhao in 2012. They proved that the two-species model has a total of 4 dynamical scenarios, as shown in the following figure. In the figure 1 and 2, it means that there is an extinction. There is a globally asymptotic stable boundary fixed point on some axis. And in the figure 3, it is bistable cases. On each axis, there is a stable fixed point. And in the figure 4, it is a coexistence case. There is a globally asymptotically stable positive fixed point in this case. The main tools for their research are based on the Floquet theory and the monotone dynamical systems theory. Some natural questions are how about the 3D cases, and in special, how does the season succession affect the 3 competing species? Therefore, we will study the 3D cases. For the 3D cases, the usually methods are based on the carrying simplex theory. So we first recall the carrying simplex, which was first developed by Hirsch in 1988. He shows that generally the competitive ordinary differential equations have a globally attracting invariant hypersurface sigma, which is a codimensional one, called the carrying simplex, as shown in the following figures for the 3-dimensional cases. The carrying simplex sigma satisfies the following 3 conditions. Sigma is a compact, unordered, and invariant subset. It is homomorphic to the unique simplex delta 2 that is x1 plus x2 plus x3 equals 1. And for it is has the attracting property that is for any non-zero initial point y, there exists a point x on the simplex such that the orbit through y, that is the phi ty, is asymptotic to the orbit through x, that is phi tx. In mathematics, that is phi ty minus phi tx tend to 0 as sorry, here is this is t at t tend to infinity. Some applications based on the carrying simplex. The first is given by Zeeman in 1993. She used the carrying simplex given a classification theory for the 3D autonomous Lotka-Volterra competitive system. And first, many researchers such as Hopper and So, Xiao and Li, Gilberger and Yan, Yu, Han, and Xiao studied the multiple limit cycles in the 3D Lotka-Volterra competitive system. Miyagishi also studied the smoothness of the carrying simplex for the autonomous competitive system. And further, in joint work with Professor Jiffa Jiang, we generalized the Zeeman's classification theory to the general 3D competitive ordinary differential equations with linearly non-clients. For the periodic competitive ODEs, Smith first proposed a conjecture that the Pancamap has a carrying simplex under some hypothesis. Further, Jiang and Wang solved his conjecture and a mild additional condition in 22. Further, Dickman, Wang, and Yang give a new result on the existence of the current simplex for the Ponca map of the periodic ODEs. Jiang, Mirjinsky, and Wang also provide the sufficient and necessary conditions on the smoothness of the current simplex.
Hi, Professor Niu Lei. Hi. Can you hear me? I have a question.
Okay.
Can you go back? Yeah, go back one slide. Why is smoothness of the current simplex important? What does that imply?
So what does the smoothness mean?
No. Why is that important? Why do people study smoothness of this current simplex?
Yeah, sure. It's a good question. Because if we have we know the smoothness of the current simplex, we can use the diffeomorphism theory on the current simplex, such as the diffeomorphism and the smooth dynamical system theory. If we do not know the smoothness of the current simplex, we can only use the topological tools to study the dynamics on the current simplex. This is from the point of view from dynamical system, and it also has its own interesting to study the smoothness of this geometry set.
Okay, thank you.
Okay. So for the general competitive maps, Hirsch proposed a claim in 28 that the competitive map has a curving simplex and some mild conditions, but he did not prove his claim. And first, Ruth Herrera gave a proof under the similar conditions. Later, with Jiang, we also give much more easier to check give criteria on the existence of the current simplex. The conditions are easier to check. Recently, Mirjinsky and Bajent also give a new proof of the existence of the current simplex for competitive maps. Based on the existence of the current simplex, we provided the criteria on the stability of the heteroclinical cycles for competitive maps of Markov type. And also we generalized the classification theory of Zeeman for 3D ODEs to the 3D competitive maps with linearly necklines, such as Leslie Gower model and the Rick models. And go back to our model. Niu, Wang, and Xie proved that the Ponca map indeed has a current simplex if the Ri is equal to Bi phi minus mu I, 1 minus phi is positive. Here Ri denotes the average growth rate. And in fact, if Ri is negative, then the species I will go to extinction. So we will study the model 1, whose Ponca maps has a current simplex, which is denoted by the set CLVS3. here we assume that the parameter Ri is positive. So in the following, we will assume that P belongs to CLV3, CLV as 3. And
sorry, why does this name mean CLVS? Why?
Sorry.
Why CLVS? CLVS, why do you have this name? C is what?
Competitive.
Competitive.
Competitive Lotka-Volterra model with seasonal succession.
Okay. Okay, thank you.
Sorry for this confusing. Okay, unlike the 2D cases, the major difficulty for the 3D cases is that we do not know whether the positive fixed point is unique or not. And our purpose is want to know how many different dynamical scenarios can occur in this site. And that is we want to give some classification on the dynamics for this site. Our main idea is that can we obtain the global dynamics based on the boundary dynamics, because on each boundary that is the coordinate plane, the system is a two-dimensional system. The dynamics on the boundary is known based on the results of Xu and Zhao. And for the 3 cases, we know that P has 3 axial fixed points denoted by Q1, Q2, Q3. And on each coordinate plane, there might be a planar fixed point denoted by VK. Of course, P might have positive fixed points in the interior of the positive cone. Our idea is want to give the classification in terms of demand classification on the autonomous competitive ODEs. So we first develop the equivalence. We call 2 maps P and P hat in the set CLV S3 are equivalent relative to the boundary if there exists a permutation sigma of 1, 2, 3 such that P has the boundary fixed point Qi or Vk if and only if P hat has the boundary fixed point Q hat sigma I or V hat sigma K. And they also have the same hyperbolicity and local dynamics. And first, the map P is said to be stable relative to the boundary of the current simplex if all the fixed points on the boundary are hyperbolic. And equivalence class is called stable if each mapping in it is stable. Under these definitions, we prove that for the site CLVS3, there are a total of 33 stable equivalence classes, which are shown in the following 2 figures. And in this figure, we show the classes 1 to 18, which do not have a positive fixed point. Here the triangle means the current simplex, and the closed dot denotes attractor. The open dot denotes a repeller, and the intersection of the stable manifold and the unstable manifold denotes a saddle. So, for example, in the class 1, this fixed point is an attractor, and the right fixed point is a repeller, and the top fixed point is a saddle. And in these classes, we prove that in fact every orbit converges to a fixed point, which denoted by closed dot. So in class 1, every orbit will converge to the left fixed point. And the results are similar in the other classes. And this figure shows the classes 19 to 33. In these classes, there we show that there has at least one positive fixed point, but the uniqueness of the positive fixed point is unknown. So we use this this circle with the dashed lines to denote an unknown region where there might be multiple positive fixed points or other complex dynamics here. So this is the classification of our the set CRV-S3, and to obtain this classification, the main tool is based on the index theory. So we first provide an index formula as shown in this theory. Assume that every fixed point OP is isolated and one is not the eigenvalue of DP set for any fixed point set. Then we prove that the following index formula holds, which shows that the sum of the index with the fixed points on the axis plus 2 multiple the index of the fixed point on the coordinate plane plus 4 times the sum of the index of the fixed point in the interior of the positive cone equals 1. Here the EV denotes the fixed point on the axis, ES denotes the fixed point on the coordinate plane, EP denotes the fixed point on the in the interior of the positive cone. So to prove this,
Niu-Le, I want to ask a question. Can you go back?
Yes.
Yes.
So
I'm curious about the second assumption. One is not an eigenvalue of a Jacobian. Which kind of a sufficient condition can I have this? How can I how can I verify this assumption?
It's a good question. If the identity matrix I minus DP set is a determinant of this matrix is not zero, then we can get this. And
in principle, I should not be able to compute the Poincare map, right? It's very difficult, I assume. Or
yes, sure. In general case, it's not easy to check this condition for the general Poincare map. But for the Lotka-Volterra model discussed in this talk, it's easy to check this condition, and in fact this condition is not needed, and by construct a consequence of functions Pn, we can show that for the functions Pn, for which one is not the eigenvalue, this formula holds. Then by the continuity of the index formula, this formula also holds for the general P. In our paper, we first used this condition, but later we thought that this condition is not needed in fact.
Oh, okay, nice. Okay, thank you.
Okay. And to prove this formula, the idea is that to use the Brauer degree theory, and we first show that there is a positive rule such that the Carrier simplex is contained in the interior of B row intersect with the positive cone, and this site B row intersect R3 plus is strictly positive under the Poincare map P. Then we reflect the Poincare map P according to each coordinate plane to get a map G defined on the whole space R3. And we can show that the degree of G on the ball below is 1 because it equal to the constant map 0. And further, we can show that the degree of G on the ball below is equal to the sum of all the index of its fixed points. So we get the index formula as shown for the the degree of G at 0 plus 2 times the degree of G at the x0 fixed points, and plus 4 times the degree of G at the coordinate plane, and plus 8 times the index of G at the positive fixed point equals 1, because according to this method, we get 2 copies of the fixed point on each positive axis, and 4 copies of the fixed point on each coordinate plane, and 8 copies of the fixed points in the positive cone. And then you are using the relation of the Poincare map P and our new defined function G, we can show that the index of P at a fixed point set equals the index of G at set. And it is easy to prove that the index of 0 of P equal to -1, then we can get the formula for P. We should give a remark that in fact for the compactive mapping, Tx given by x1, f1, x2, f2, x3, f3. A similar index formula has been proved in our previous paper, and an additional assumption you recorded the total computation as in ODEs. That is the per capita growth function fi is decreasing with each xj, and that is partial fi over partial xj is negative for any ij from 1 to 3. In fact, this assumption can enable us to construct a competitive vector field so that we can use the Poincare-Hopf theorem to get the index formula. But for the Poincare map, this condition is not easy to verify. And in most cases, and this condition is does not hold for a periodic competitive ordinary differential equations. So we give a new approach to proves a similar index formula for our Pankama map. And then next, we study the boundary dynamics. And first, for given boundary fixed point set, we can calculate that lambda I set equals exp ri minus j from 1 to 3 aij theta j hat is an eigenvalue of dp set for any I not in its support. So here the set j hat is the average of the solution psi t set on a period from 0 to omega. This is the average. So it is easy to calculate this eigenvalue of the boundary fixed point set. And we let gamma ij equals aii rj minus aj ri. And in fact, we can show that the eigenvalue lambda j for the fixed point qi is greater than 1, respectively less than 1 if and only if this value gamma ij is positive, respectively negative. And first, gamma ij, gamma ji is positive, implies that the determinant of the submatrix aii, aij, and aj, ajj, that is this value is non-zero. So we in this case we have generally we have a plenary fixed point, and let beta ij equals ajj ri minus aij rj over aii ajj minus aij aji. This is the coordinate of the planar fixed point v k, and we have the following stability of the boundary fixed point if gamma ij is positive, respectively negative, then the axial fixed point qi repels, respectively attracts along the boundary of the current simplex in the coordinate plane pi k. And moreover, if both gamma ij and gamma ik are positive, then qi is a repeller on the simplex. And if they are negative, then qi is an attractor. If gamma ij and gamma ik are different signs, then qi is a saddle on the simplex. And qi is hyperbolic if and only if gamma ij times gamma ik are not zero. And for a planar fixed point vk, vi, if gamma jk times gamma kj is positive, then there is a unique planar fixed point vi. And moreover, if these values are negative, then vi repels along the boundary of the current simplex. If they are positive, then vi attracts. In this slide, we want to show that in fact the stability of the boundary fixed point can use in a geometric method. We defined Ri to be the plane denoted by aii xi plus aij xj plus aik xk equal to Ri. And R3 plus minus Li can be divided by two components Vi and Bi. Here, Ui is unbounded components and Bi is bounded components. For the x-real fixed point Q1, Q2, Q3, and we denote Qi hat to the integral phi psi t Qi, which is equal to the integration from 0 to phi omega of phi t L Qi. And Qi hat is just the intersection of the plane Li and the xi coordinate axis. So we can get the expression for these three values. Q1 hat is equal to R1 over A1100. Q2 hat equals 0, R2 over A220. Q3 equals 00 R3 over A33. And similarly, for Vk, we can also define Vk hat. And Vk hat is just the intersection of Li, Lj, and the coordinate plane pi k. That is the solution of Av hat tau I equals Ri. And here is a parameter matrix of Aij. P might have a positive fixed point P in case Li, Lj, and Lk intersect in the positive cone. And Rij is negative if and only if Qi hat is in Ui, and it is positive if and only if it's in the Bj. The dynamics of Qi along the boundary of the currency plex on the coordinate pi k can be determined by the position of the Qi hat relative to the line Lj capital of the pi k. And similarly, for the stability of Vk, it can also determined by the position of Vk height relative to the line of Lk. That is whether it belongs to the bounded coordinate bounded part Bk or the unbounded part Uk. Then P is stable relative to the currency plex if and only if all these values of gamma ij are not 0 and AKI beta ij plus AKJ beta ji not equal to RK. And to classify this set, next idea is to construct an auxiliary system that is Lestigar map, because which has the same parameters Ri and Aij given by the above equations. And we denote by CLG3 to all the 3D Lestigar maps. We note that the point map P has a fixed point Qi or Vk if and only if the Lestigar map SP has a fixed point Q star I or a planary fixed point Vk star. Qi or Vk has the same hyperbolicity or local dynamics as Qi star, this is a V star under the elastical member SP, and they are equivalent relative to the boundary dynamics if and only if two elastical maps SP and SP height are equivalent relative to the boundary dynamics. And we have proved that there are a total of 33 stable equivalent classes in CLG3 in our previous work. So we obtained the 33 stable equivalence classes in the set of CLVS3, as shown in the two figures. And we want to point out that in the class 27, the boundary is a heteroclinic cycle, and we do some numerical simulations, and we found that there in fact there exist invariant closed curves in classes 26 and class 27, and this is orbit for their Planck maps, which is invariant closed curve, which denotes the quasi-periodic solutions in the seasonal model. And further, if we know the uniqueness of the positive fixed point, we can also obtain the global dynamics in some classes. For example, if the classes 19 to 25 have a unique positive fixed point, then we can show that in these classes, area orbit can converge to a fixed point, and then the whole dynamics on the current simplex is shown in this figure, and in the interior, the unique fixed point is a saddle, and the intersection of these two figures are the stable manifold and the unstable manifold. And this result can follow from our previous work joint with Ruth Herrera and Mir Jinsi, and we prove that for rotation preserving homomorphism on a topological disk D into itself, which has only finitely many fixed points, and the unique fixed point in the interior has index -1, then area orbit OF converging to some fixed point. Because the current simplex is a topological disk, and the restriction of the Planck map on the current simplex is rotation preserving, so we can obtain the results for the classes 19 to 25. Based on the index formula, we can show that the unique fixed point in the interior is -1. And for the class 33, if the fixed point is unique, then it is also globally asymptotically stable. And this conclusion can follow from the previous work joined with Gillenberger and Chiang. Also from the similar work of Braulier, Elidi, and Luis. And in that paper, we show that for a map from a box 0 to U maps to 0 to U, and if the determinant of dtx is positive for area x, and the inverse of this matrix is positive, and on each coordinate plane there is a unique positive fixed point vi, which is globally asymptotically stable in this interior of pi I, but a saddle for the T in the whole space. and T has a currency pax, then P is globally asymptotically stable in the interior of Rn plus.
Sorry, Niu-Le, so how do you prove the global stability here?
This result is generally using the idea or the work of Braria, Elidi, and Lewis. They show that for a competitive map, a surface with positive the idea is that a surface with positive
so my question is, do you need any monotonicity, like from the Lyapunov function or from some monotone dynamical system, or it's another kind of proof?
Yeah, the idea is mainly based on some techniques like the monotone dynamical system to prove this.
But this system is not monotone, right? It's not.
Sorry?
Is this system monotone?
This is a competitive map, and
competitive map is
competitive monotone, but they can generate monotone monotone sequence on surfaces, and it can prove that the surface convergence, and
okay.
So okay, so we know that the uniqueness of the positive fixed point corresponds to the uniqueness of the positive harmonic periodic solutions of the model. Point seat is a positive fixed point if and only if this integration is a positive solution of the linear equations AXI equals RI. But the question is when the positive fixed point is unique, and whether this model has always has a unique positive fixed point when it exists. So in order to study these questions, in fact, this is very difficult. So we first consider a special case that is mu I are the same constant mu, and all bi are the same constant b. Then the model 1 can be described by the equation 5, for which all the mu I are mu here, and all the bi are b here. Here, now the linear map Lx can be described by the constant L multiply x with L equals E minus mu 1 minus phi omega. So all these notations are similar as in the general model. And now we consider the one-dimensional logistic equation 7, which and also the logistic equation with seasonal succession given by 8. And we denote by M to be the Planck map of the equation 8. And similarly, it can be written as rho phi omega Ly. And it is easily to solve that M has a unique globally stable positive fixed point, which is described by rho star E9. And the condition is that the average growth rate R is positive. And now we can in this special case, if R is positive, we can prove that the discrete orbit pkx can be written as rho star times phi k rho hat from the point initial point x over rho star. Here the rho hat is integration of the solution from the initial point rho star, which is given by r omega over b. So we establish the relation of the discrete orbit pk with the solution of the autonomous Lotka-Volterra model phi. And then we show that point x star is a fixed point of P if and only if phi rho hat x star over rho star equals x star over rho star. That is, x star rho over rho star is either an equilibrium of the LV system phi, or it is a periodic point with period rho hat. Further, we show that P has a unique positive fixed point if and only if the linear system AXI equals B has a unique positive fixed point and either one of the two conditions holds. The first one is that the autonomous LV system has no positive periodic orbit. The second is that if phi has a positive periodic orbit gamma, whose period is denoted by T gamma, satisfy that omega over T gamma equals a number Q times B over R. Here Q should be a non-integer. And if suppose that phi has a positive periodic orbit gamma, and P has multiple positive fixed points if and only if omega over T gamma equals an integer K times B over R. In particularly, if the autonomous LV system has no periodic orbit, then the Poincare map P has at most one positive fixed point. And if phi has a periodic orbit gamma, whose period is T gamma, and we let omega over T gamma equals zeta times B over R, then it is shown that rho star gamma is an invariant closed curve for the Poincare map P, and if zeta is an integer, then rho star x is all fixed point of P for any x on this periodic orbit, and zeta is rational, then every orbit on rho star gamma is a periodic orbit. If zeta is irrational, then every orbit on rho star gamma is a dense orbit whose omega limit set is this invariant closed curve rho star gamma. And zeta is a rational number corresponds to that the system has subharmonic solutions. Zeta being is irrational corresponds to the solutions are quasi-periodic. And as a contrary, we can show that classes 19 to 25 and 28 to 33 indeed have a unique positive fixed point in this special case. So every orbit converges to some fixed point. And for classes 26, there are 3 different cases, depend on the number zeta. defined by beta 1, beta 2, beta 3 minus alpha 1, alpha 2, alpha 3. If the Z is non-zero, then there is a unique positive fixed point in class 26. If zeta is 0, then there is a heteroclinic cycle filled with a family of invariant closed curves around a positive fixed point, as shown in the figure B. Here, this triangle forms a heteroclinic cycle. In the interior of this triangle, there is a family of invariant closed curves. And in case A and case C, there is a unique positive fixed point. If zeta is negative, then the positive fixed point is stable. If zeta is positive, then this fixed point is unstable. And the cases for class 27 are similar, which depend on the value of zeta. If zeta is non-zero, then there is a unique positive fixed point. And if zeta is negative, then P is globally asymptotically stable. While if zeta is positive, then the boundary is globally asymptotically stable, which is a heteroclinic cycle, as shown in the figure C. That is every orbit in the interior, except this positive fixed point converges to the boundary heteroclinic cycle. And similarly, if zeta is 0, then in the interior of the Corinth-plex, there is a family of invariant closed curves around a positive fixed point, as shown in the figure B. So we proved that in fact, for this special case, that is mu I equals mu and bi equals b, there are exactly 33 different dynamical behavior in this site. And this figure shows the first 25 dynamic scenarios. In these classes, every orbit converges to a fixed point. And these figures show that for the classes 26 to class 33, we show that for class 28 to 33, the positive fixed point is unique. So the dynamics, there is only one dynamics in each class. For class 26 and 27, each class has 3 different dynamics, as shown in A, B, C respectively. And and we should remark that for the class for the case 26B and 27B, there is invariant closed curves. On these curves, every point might be a positive fixed point, depends on whether the number z is integer or not. So, and we indeed can give gives concrete examples that that can be integrated. So we indeed proved that for this model, that the positive fixed point indeed can be non-unique. That is, there might be multiple or infinite many positive fixed point in the interior for this model. So this is my talk. Thank you very much. This is some references. Thank you very much.
Thank you very much, Niu Lei, for this very nice and beautiful and deep talk, I would say. Okay. So any question, comments, remarks from the audience? Please just unmute your microphone and ask. Sorry. Yes, any questions? Maybe let me begin with a question. I am thinking, so you have a non-autonomous omega periodic OD system, right?
Yes.
And suppose I consider the omega average system. I take the average of the coefficient. Okay. Then what kind of figures in your classification remains survive? Have you ever thought of this question?
So
I mean, your analysis, your results are much more stronger than I ask. But I am curious, what kind of figures in your picture can survive under average?
Okay, this is a good question. Sure, yes, we can define the average systems for this periodic system, and then we can use the similar classification method for the autonomous average ODE system, and also we can show that the similar 33 classification classes for this average system also the same, but
they all survive. They all survive.
Yes, they all survive.
Really?
Yes.
Interesting.
Yeah.
But if they all survive, then why don't you just study the average system? You know?
Yeah, sure. Yes, but yes, we can also study the average system, but they are two different systems. We should prove or establish some relation between these two systems.
Yes.
Yes. We can study this average system, but whether this average system can see some long-term behavior of this periodic system or not, there is no general results between them. But based on these studies of these two systems, we can see that indeed they have the similar dynamics because on the boundary of the carrier simplex, they share the same dynamics information between these two systems, but in the interior they are totally different. For the average autonomous ODE system, the positive fixed point is generally unique, but for this periodic systems, the positive fixed point is can be non-unique, and there might be quasi-periodic solutions for the periodic system, but for the autonomous average system, there is no quasi-periodic solution. Only periodic solutions can occur. So it is still an interesting question to study the relation between these two different systems, and I think for this system, they can share some similar information, but for general periodic differential equations and the average autonomous differential equations, there might be no similar dynamics in general.
Mm-hmm. Yeah, thank you very much. Yes. And yes, questions, comments. Okay, I have one more. Okay, I'm very curious.
So
Can
please.
you go back to your slide about LO, this function LO, exponential of minus mu j something?
So for which one?
I think you have a transformation LO, capital LO.
Capital. Oh, okay.
At the very beginning of your talk, yes.
This.
Yes, here. I think this function LO is like because this exponential minus something is the solution of this linear part of the equation, right?
Yeah, sure.
And in your Pangai map, I mean, you shift your solution by this exponential decay solution and match to the other Lotka-Volterra part. I think this is very smart. So that's why your Pangai map can be reduced to study the composition with the Lotka-Volterra flow and this LO. This is super smart, I think. And
Yes.
but I am curious whether this LO is very necessary. Suppose I change your first equation, like another minus mu x, but the same Lotka-Volterra system, but different competition rate, different growth rate.
Okay.
So suppose now your EA, equation 1A, is another Lotka-Volterra system, but different growth rate, different competition rate. Can you still apply your result?
Sorry. So do you mean that in
my model assumption is there are two seasons, winter and summer.
Okay.
And this species they always compete. But in summer and in winter, they just have different competition type.
Yes.
But it's not like the linear decay equation you consider. I mean, then can you still have similar result or similar technique?
So yeah, it's indeed good questions, but I think there the method can also be used to study these cases, but generally I think the results might be different. And
I think so. Yes.
Yes, because the difficulty is that to prove the uniqueness of the fixed point in the interior of the bound in the interior of each coordinate plane. In general, even for the two-dimensional cases, the uniqueness of the positive fixed point is not easy to prove. It depends highly on this linear equation, and so if the growth is given by other growth functions, I think it's also very difficult to prove the uniqueness of the positive fixed point for even the two-dimensional cases, and for the 3D different 3D cases, I think it's much more difficult. But the method can also be used to study. the idea is similar to using the boundary dynamics to study the dynamics, but there are some difficulties here.
Okay. Thank you. Cool. Yeah. Good. Other question, comments?
Hello.
Yes, please.
May I?
Yuki from Japan.
Maybe I missed some explanation.
Do you want to show your face so that everybody can see?
Yes.
Yes. Hi, Yuki.
Hello. So, can you determine dynamics for given parameter from your methodology?
Yes.
Sorry.
Yeah, I would like to know that you can determine the classification or the dynamics or given parameter of the model.
Okay, sure.
If so, I would like to know how to do this.
Okay, yeah, good questions. The idea is to give the study of the boundary dynamics, because the system restricted to the boundary, that is each coordinate plane is a two-dimensional system. For a two-dimensional system, there are much little parameters, and we can usually give the explicit classification of the dynamics with respect to the parameters. And then we use an index formula, which is establish the connection of the boundary fixed points and the positive fixed points. And that is, we can use the existence of the boundary fixed points and its stability to determine whether there exists positive fixed point or not. And the other main idea is to classify how many different boundary dynamics can occur in the 3D cases. This is just some basic calculation for how many different cases for each boundary fixed points, how many different stability cases for each one, and we can calculate all these boundary all these cases of the boundary fixed point, and then using the index formula to get the information in the interior of the simplex.
So I think, Yuki, to my understanding, everything is from the local information at the boundary.
Yes.
So given parameter, you can calculate the existence and stability of a boundary equilibrium.
Okay.
And then this determines which type of the figure this equation belongs to, I think.
Yeah.
Okay.
Yeah, this is the idea. Yeah.
But still there seems to be a problem to know the, for example, the uniqueness of the positive point. Since you study somehow the boundary dynamics.
Okay, sure, that is, yeah. So this method does not depend on the number of the positive fixed point, because we only study the boundary. Then we want to obtain the information of the positive fixed point by the boundary dynamics. So so we give index formula to study the interior according to the boundary.
Okay. Thank you. I got something. Thank you very much. Thank you.
Yeah, very good. So, other questions, comments? Okay, if this is not the case, let's thank the speaker, Professor Niu again. Thank you.